Hi, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology. What I'm going to do in this video is build the case that we are in a climate change emergency. So I'm going to build a scientific case showing how our climate system is changing in 2016 and why scientifically we're in a climate change emergency. We have to declare this politically on a global basis. And then how do we deal with this problem? We need to deploy the three-legged bar stool survival techniques as soon as possible on an emergency basis. And first what I'll do is build the case for the emergency, and then I'll discuss briefly some of the possible things that we must do. So our fossil fuel combustion has increased. We've also increased the land use changes, less forests, more urban areas and agriculture. So our greenhouse gas levels are rising quickly at an ever-increasing rate, at an exponential rate. The Earth is rapidly warming. Therefore, we're getting a rapid decline in Arctic sea ice and snow cover, and we're getting faster Greenland ice cap melting. So the Arctic surfaces in the entire Arctic region are becoming darker. They're absorbing more sunlight. This is causing the northern regions to warm faster than the global average by 5 to 8 times. This decreases the equator to Arctic temperature difference. Less heat moves from the equator to the pole in the atmosphere and in the oceans. 2/3 goes in the atmosphere, 1/3 in the oceans. In the atmosphere, the jet streams are slowing, becoming wavier and often stuck, causing extreme weather events to be more frequent, stronger, to last longer, and to occur where they never used to. In the oceans, we're getting warming and thus stratification and acidification that's killing off marine life throughout the food chain, starting at the base of the food chain. It's reducing oxygenation and vertical mixing in the ocean. Currents such as the Gulf Stream are slowing down. We're getting large sea level rise also that is starting to flood coastlines. The climate system of the Earth is many different components. We have our hydrosphere, our lithosphere, we have the human influences. We're part of the biosphere, humans are part of the biosphere. We have the atmosphere, of course, and we have the cryosphere, the ice sheets and so on. So we have these 5 main components. We have the greenhouse gases in the atmosphere. We have solar input coming into the system. If one thing changes, then it ripples through and changes other things. We need to consider the Earth as a climate system and look at how the different components are changing. I did a number of videos just a few days ago. Even in a few days, things have worsened significantly. So the overall Arctic region is 7.23 degrees Celsius warmer than normal. This is the anomaly. Most of the heat is in the Arctic, although we're also getting massive heat anomalies, temperature anomalies, up to 20 degrees Celsius in the Arctic and 10 to 15 in North America. The only cold spot is in Siberia, and that is being dissipated. So the whole climate system is messed up. There's no other way of putting it. It's really acting strangely. What is happening is there's an equalization of temperature with latitude. The high latitudes are warming so much, we're getting an equalization of temperature, which changes the weather patterns and the climate on the entire planet. This is another view, and you can clearly see the Siberian cold spot here, the very warm spots in the Arctic and over eastern North America, and we have colder regions in western North America. So we're getting a breakup of stable climate patterns with latitude around the globe. We're getting this patchy sort of areas where we have warm areas and warm areas and cold areas. And those areas, because there's large temperature differences over small distances, for example, here to here, then this causes very high winds and lots of storm activity. Look at the oceans. The oceans are reflecting what the atmosphere is doing. North Atlantic, all of these regions are warmer than normal. The Arctic is very warm, especially in the North Atlantic, and also on the Pacific and the Bering Strait side. And recently we had a very, very cold spot south of Greenland. Now we have this very, very cold spot in the North Pacific. So we're getting very unusual behavior in the atmosphere and in the oceans because the heat transfer processes of heat from the equator to the Arctic are completely changing. So the greenhouse gases, methane and CO2, are the most important ones that are rapidly increasing. Water is also increasing, water vapor rapidly. It's a feedback to the climate system. But we're off the charts. If we go back almost 1 million years, we're off the charts with these two greenhouse gases. And I pointed out, and I'll reiterate the importance of this. This is very important that the CO2 this year is expected to rise about between 4 and 5 parts per million, off of the chart. So the CO2 is rising rapidly. The methane is rising extremely rapidly, mostly in the Arctic, and I'll discuss that further. Nitrous oxide also increasing rapidly. This is the rates of change each year, and this is the overall cumulative increase. The worrying thing is atmospheric rise is expected to be between 4 and 5 ppm this year, but CO2 emissions from humans is expected to be similar to last year, which was similar to the previous few years. So the last 4 years it's flattened out, but this is very bad news if this data is correct. It's great that the planet is coming together and cutting emissions, but it's very bad news that the atmospheric levels are still rising so fast. This seems to indicate that the global sinks are likely failing. And the biggest global sinks would be the Amazon rainforest. We're losing a lot of the forest due to drought and fires. We're losing a lot of the boreal forest due to fires. There's over 100 million trees, I believe, that have been dying across North America due to pests and drought and water stress, very high temperatures. The ocean is stratifying and warming, so it's not absorbing as much CO2. There's not as much vertical mixing, so there's less CO2 going physically dissolving into the water at higher temperatures. There's also less phytoplankton growing because there's less vertical mixing, so we're getting all of these cascading feedback effects that are becoming extremely serious and cannot be ignored. So the mean surface temperatures are skyrocketing in 2016. They're going off the charts. If this isn't a climate emergency, I don't know what is. If this doesn't move people to action, I don't know what will. This is February of this year. The numbers I've corrected were basically 1.95 degrees Celsius, so almost 2 degrees above the pre-industrial levels in terms of temperature, the pre-industrial being 1750. So February, off the charts. March, off the charts. This is completely just devastating the Arctic sea ice and snow cover. These are the IPCC models, the mean and the spread of the models, and this is what the observations are showing. So let's have a look in more detail at what the sea ice is doing. So this data is updated as of very recently, and we're seeing an exponential decline. If these are different types of fits, these are the exponential fits. So we go to zero around just after 2020, say 2022 or so, according to this data. It's not just September, which is the minimum is being reduced. This is September. Then October and August are bracketing it. and then the next 2 months are bracketing it, and so on. Every month is coming down, and what we're seeing right now in October and November of 2016 is those particular curves for those particular months are converging, are dropping downwards even faster than the September minimum is dropping. So we're always discovering new phenomena occurring in climate change. We're just seeing it happening real time. This is the Arctic sea ice extent. A couple of days in the video, the curve looks quite different. If you compare this curve now, we've actually seen a flattening off. We've actually seen sea ice extent dropping. 50,000, 50K on one day, and I think up 146K or something on another day, which is, we just haven't seen this before. The sea ice tries to grow and extend out, and it's being chopped off by wave action, by very warm water temperatures, and also by the blowtorch-like temperatures that are coming into the Arctic, and the huge Arctic-wide temperature anomalies of 20 degrees C or 36 Fahrenheit above normal for this time of year. So this is the temperature of the Arctic region north of 80 degrees. And this curve is even worse than from a few days ago. Look at the spike up here. Like, this is just incredibly, this is unbelievable. This is unheard of. So this temperature for this year compared to the long-term average is about 20 degrees Celsius above average. It's essentially summer in the Arctic right now in November. This should be headline news around the world. It's starting to make some mainstream newspapers and articles online, but they just don't get it. They just don't get that their lives and their children's lives and any future for humans on this planet are being threatened by what we're seeing here. We're going into very unknown sort of territory where our food supply is going to be severely stressed. I mean, this just blows me away. It blows any climatologist away. Should blow everybody away. It will soon. Antarctica, the drop below the long-term average and the variation is accelerating. We're many standard deviations below, and we're heading down more steeply. Whereas just a few years ago, we were at record amounts. So we're getting, this is all indicative of global weirding or climate weirding. This is one of the most scary plots, because if you add the global sea ice area in the Arctic and Antarctic, we're flatlining here. We're leveling off, we're flatlining, and this is amazingly, this is unprecedented. This is what the ice looks like on maps. So the red line is the norm, the medium from 81 to 2010 in both of these cases. The red line, the yellow line. Okay, so we're missing vast amounts of sea ice in the Arctic and in Antarctica, and there's even big gaps in Antarctica here, which is also very surprising, very unusual. This is the Arctic monthly, average monthly Arctic sea ice extent for October, and you can see how we've fallen off a cliff here. There's many ways to look at this data. This is another view of October, comparing Octobers from 79 to 2016, and we've dropped off a cliff here. Or we can talk about the Arctic sea ice death spiral. So what we're seeing is years here along the radial axes to 2016, and each curve is the different months of the year, with September being the black one, and then the months October and August bracketing it. And we're seeing when this heads to zero, so I would expect this to head to zero, the black line, by say 2020, and then the other two lines to head to zero on either side by about 2022, and then these next two lines by about 2024, and then all of the lines heading to zero by 2030. And then we'll basically have no sea ice in the Arctic year-round. We'll be in a much warmer climate. Who knows? Global average temperatures could be 5 degrees, 6 degrees warmer than what they are now, and we'll be in a Hello, I'm Paul Beckwith. I'm at the University of Ottawa with the Laboratory for Paleoclimatology, and this is a continuation of a series of videos on our climate change emergency and what we have to do to deal with it. So, the Arctic sea ice is undergoing a death spiral right now. So, September is the black, and then the two lines here, the blue and the purple, are the months bracketing September. And then if you go out another 2 months on either side, you get these here and so on. So what's happening is the ice is spiraling to zero very, very rapidly. And in the very near future, matter of years, I'm expecting to see the first blue ocean event where there's no sea ice, where the black line goes through zero. So why is the ice suffering so much right now in October and November? And this is the main reason. We're seeing Greenland's up here. This is the Atlantic side here, and this is the Bering Strait, and Alaska is over here. So we're seeing the ice being attacked on both sides here by very, very warm air coming in. So if you take the average temperature anomaly relative to the long-term climatological mean, these temperatures up here are 7, 8 degrees. Anything orange and above is 6 degrees warmer than normal for the entire month over these regions. So just imagine the melt that's going on in Greenland here, which is raising sea level. And imagine what is happening to the ice as it's circulating through the basin, through these warm areas. It's just not able to grow in its normal positions because it's just being cut off by this very warm water, and since the ocean is open, there's very strong wave action, which is also mixing up the very thin ice, ensuring that it can't expand to its usual levels. This is the air temperature anomaly in October. So what we have here is, this is the surface down here, 1,000 millibar. So we get very warm, above 6 degree temperatures, and then we go to the orange, which is 5 and above, and this is going up. So this is about 1 kilometer in the atmosphere. For every 100 you drop here, you go up another kilometer. So this is 1 kilometer high, 2 kilometer high, 3 kilometer. This is about 5.5 kilometers high, and so on. So we get to the top of the troposphere, which is very low at the Arctic. It's about 7 kilometers here. So the entire troposphere is showing warming here in the whole northern region. This is 66 north to 90 north. So this is the North Pole. So you can see how the atmosphere is completely warming because there's a lot of heating on the surface, and it's propagating up into the atmosphere. So there's loads of daily information on Arctic sea ice. So I've shown previously the sea ice thickness here. The only thick ice is pushed up against the Canadian archipelago. This is much different from just a few days ago. So what we see here, the motion of the air circulation is pushing the ice around. So this is the motion. The arrows are going this way, so the ice is cycling this way. So this ice, and it's at the maximum speeds. This is 30 centimeters per second drift of the sea ice, and we're seeing how it's being driven. The ice, the thick ice that's along the Canadian archipelago, is being driven out into the Atlantic Ocean, where it's destroyed by the warm water temperatures. So this is why the sea ice volume has stalled. It's not growing. We're getting huge export here. We've got the warm water coming in both sides, and I show some data here. So this is again the ice thickness here. This is the sea surface temperature. So it's all above zero here, basically, and so water freezes. Seawater freezes at -1.8. That's if it's 35 PSU salinity. So you can see there 2 to 4 degrees is the blue. You can see the warm water impinging here, and the water here is so the ice is being surrounded by warm water, which is really restricting the expansion of the extent and area this year. And in fact, it declined in the last few days, the extent, which we haven't seen. This is November. It should be like forming. This is sea surface salinity. So you can see, when there's a lot of melt, there's a lot of fresh water. And there's an awful lot of fresh water on the edges. So this sea ice, as it's trying to expand, it's hitting the warmer water on the surface. It's melting. That creates fresher water and a lower salinity on the edges. And there's also wave action. So if there's 3-meter waves, then that's propagating downwards and affecting the mixing down to much, much deeper levels. And the water is warmer underneath. So that warm water is coming up from the mixing, replacing the water that has melted the previous ice. So this will keep going until the water cools down through the water column. This is sea surface height. Colder water is denser. That will be a lower sea surface height. Warmer water expands, it's higher. So this is sea surface height difference. So the red here is plus 60 centimeters, 0.6 meters, about 2 feet. The purple here is about minus a meter or minus 3 feet. So in other words, the surface of the ocean, where the water is coming in from the Bering Strait, from the Pacific, is 2 feet higher than, it's actually plus 2 feet, this is minus 3 feet. So the difference from here to here is about 5 feet. So the water, of course, flows downhill. The water, that brings in more warm water from the Pacific flowing through into the Arctic region, underneath the ice that's there. And so the ice it's being attacked from above by the very warm air temperatures. It's being attacked from below by the very warm water temperatures. And it's being attacked on all sides by wave action and very warm water. So if this trend continues of sea ice loss, there's a high probability that the first blue ocean event will occur, I think, 2020 rather than 2022. This ice-free duration would be less than a month in September, and then it extends to 3 months. So August, September, October, ice-free by, say, 2021 or 22. 5 months, no Arctic Ocean sea ice, so July, August, September, October, November by about 2023, and all year, gone all year by 2030. This is what I expect with these enormous feedbacks. One of the main feedbacks to get rid of the ice is the albedo. But once the ice is gone, and as it's going, it's a latent heat feedback. So it takes a lot of energy to melt ice. And when you melt the ice, you end up with water at 0 Celsius. So the temperature doesn't change that much. Get rid of the ice and the temperature will skyrocket, because to melt 1 kilogram of ice, you need a lot of energy. Apply that same energy to 1 kilogram of water at 0 Celsius, just above freezing point, and that water will raise up to 80 Celsius. So we won't see 80 Celsius water on the surface of the Arctic because it mixes and it'll warm the water down below. But it just gives you an idea of the huge feedbacks. I mean, the warming in the Arctic is going to skyrocket when we lose that sea ice. The snow cover, as everybody talks about sea ice, but the exponential decline in the sea ice, but the Arctic spring snow cover is declining twice as fast as the sea ice. And you can see here, this is a deficit of snow in the Arctic, northern hemisphere, in the spring, in June. This is contributing just as much. This is decreasing the albedo, or making the Arctic darker, at an even faster rate than the sea ice is doing, for the spring months. So Greenland's up there. The melt of Greenland is going to greatly accelerate. We've actually seen melt over almost the entire surface of Greenland already. This is going to become more and more common. And the albedo of Greenland is dropping because of surface meltwater ponds. As the ice melts back, it uncovers and concentrates dirt on the surface. And we also get tremendous amounts of ash being delivered to the Arctic from northern boreal forest fires. So massive fires in Siberia and northern Canada. The ones in Siberia specifically are not, a lot of them are just left to burn, and that ash is going up into the Arctic by this very wavy jet stream, which is carrying not just warm air but also ash So it's accelerating to the loss of ice. So we have all these cascading feedbacks in play. Worldwide disasters are rising due to climate change. We've got hydrological, we've got more storms, we've got heat waves and things. Those are all adding up and increasing. And also you can make a case that geophysical events will also increase under rapid climate change. So sea level is going to have a huge impact on humanity. Most of the sea level rise is from expansion of water, more glacial melt, and ice cap melting. Present rate 3.4 millimeters a year. Projected rise about a foot by 2050, up to 2 meters or over 6 feet by 2100. I think these are all underestimates. I expect maybe 7 meters by 2070 if these exponential rates of Greenland and Antarctic ice mass continue. In the 121,000 years ago, in the last warm period, the sea did rise 2 inches per year for over 50 years. That's 5 centimeters per year. So the system is capable of having very, very rapid sea level rise. The oceans are stratifying and becoming more acidic. The acidity has increased about 30% in the last 3 or 4 decades, and this is going to severely impact the base of the marine food chain. So there's albedo flipping in the Arctic. Right now, the sea ice forcing gives about 0.1 watts per meter squared if you average over the Earth, and that will increase to 0.3 times when the sea ice is gone for the first month, first blue ocean event, say by 2020. And when the sea ice is gone year-round, it's 7 times the forcing right now. So this is the rate of warming in the Arctic is now about 2 degrees Celsius per decade, 6 times the global rate. That will increase as the ice vanishes due to all these cascading feedbacks. There's huge amounts of methane in the Arctic. So 1,700 gigatons on land, 1,750 under the sea in the eastern Siberian Arctic shelf permafrost. 50 is in precarious state in the very top layers. It's liable to have a sudden release. We've had 5 gigatons in the atmosphere today. So even if 15 gigatons went in over 10 years, that would dominate CO2 forcing, leaving absolutely no chance for 2 degrees Celsius stabilization, let alone 1.5. So despite our efforts, they're too little, too late. We have to step them up correspondingly. So, if we had this release of the 50 gigatons, levels of the methane in the atmosphere would go up 11 times, catastrophic feedback loop, warming would spiral up, world food production would spiral down, geopolitical unrest and countries collapsing would make it a very nasty place on our planet. And this shows where the eastern Siberian Arctic shelf is, right across from Greenland here. So the methane levels globally are rising. They stabilized off here, but they started rising rapidly in 2007. There's an awful lot of fracking and leakage rates, but there's also more coming from the Arctic now. So the methane from the seafloor in the Arctic, up to now, it's been quite small, 10 to 20 megatons. Over the last 5 years, there's been a rapid escalation. The region to watch, again, the eastern Siberian Arctic shelf, one of the largest continental shelves on the planet. There used to be ice over there. Now it's very much open for long periods of the year. So the water's warmer. We're getting these plumes, tens of meters in diameter a few years back, and then within a year or two after that, remeasured hundreds of plumes as large as a kilometer in diameter. The area ratio is 2,500 times larger. That would be the methane coming out ratio as well. So this is where the methane is. We have it in cloth rate. We have it in the permafrost. As the water is warming, it perforates the permafrost. We get methane going up through the water column. We're measuring higher levels of methane in Barrow, Alaska, also in Svalbard. So the methane is being detected to rise at surface levels across the Arctic. This is where the methane is. This is International Permafrost Association. So we have continuous methane, it's the dark purple, going to discontinuous, sporadic, and isolated. So it surrounds the Arctic region. We're warming this region like crazy. Of course, there's going to be this Hello, I'm Paul Beckwith, University of Ottawa Laboratory for Paleoclimatology, and this is a continuation of previous videos, and I'm talking about the permafrost, the terrestrial permafrost up in the Arctic region. So you can see surrounding the entire Arctic Ocean, there's continuous permafrost as furthest north, and then sporadic as you go further south, discontinuous as you go further south, and then sporadic as you go even further south, and isolated patches. And the Arctic is a region that's warming faster than any other any other region on the planet, and it will thaw the permafrost, releasing CO2 and methane. So this is part of the process. This cartoon shows how we have it, with the permafrost intact, we can have a neutral carbon balance, some coming in, some going out, with plant respiration, for example. As we get warming and starting to thaw, the plants are growing faster, and there can be some more respiration of older carbon. As we get even warmer, there's a lot more carbon out than in. We get capture of carbon with the vegetation, but we get a lot more coming out of the permafrost, the thawing permafrost, as indicated by the larger red arrow. So that's on terrestrial. Under the ocean, we have the permafrost extends down, and we have hydrates, which is a lattice of crystalline water, if you like, ice, surrounding methane. And when the ice cage thaws out, the methane is released. There's an expansion of about 160 plus times. It builds up the pressure underneath, and then it bubbles up and comes up through the water column. If the water is shallow, then the water column is quickly saturated with methane, and then the rest of it will get up into the atmosphere. So if the water column is very deep and there's small trickles coming out, it'll be absorbed completely in the water column, not reach the atmosphere. But if there's a burst, it'll quickly rise up and go into the atmosphere very quickly. So this just shows methane. This is just over 6 years, same time each year, same time it's the 12th month, so December each year. And what you can see is, the red is the methane. This is a concentration, the color map, and you can see a huge uptick of methane. This is in 2011 compared to previous years. Since 2011, here's another view, different time of year. You can also see a very large increase of methane. Over 5 years, showing a large increase near the sea ice, and it's harder to get more recent data like this. So the Arctic warming is changing the jet streams. Like I said, this is a more typical jet stream configuration. The jet stream is basically the white area in between the other two colors. So you can see it's mostly circumventing the North Pole, whereas here it's much wavier. There's very deep troughs going deep south, and there's ridges going up fairly high north. So we're seeing this this type of configuration. This is 500 millibar geopotential height. So, but it indicates temperature, basically colder areas and warmer areas. So you can see there's a huge difference. The jet stream is slowing down, becoming much wavier, and causing problems. So here's a side view of an exceptionally wavy jet stream. And this is the jet stream hooks back and comes around, and it was like this for many days. In June of 2013, there was tremendous torrential rains. It flooded out downtown Calgary, and insured costs exceeded $6 billion. So you can look at all of these extreme weather events, and you can relate them to what the jet stream is doing for the most part. This is a deadly heat wave that killed 70,000 people plus in a matter of weeks to a month in Europe. Most of these deaths were in France. This is the heat wave here, which was persistent over lots of Europe, and people just weren't prepared for it. So the root cause was a wavy jet stream, or wavy and stuck persistent ridge. So there's very real implications of everything I talk about here, and they're going to explode. They're going to get a lot worse. So this is a drought. This is an indication of projected drought over the planet in about 40, 50 years. And you can see these areas are becoming much drier. So the purples, these areas, the purples, the oranges, the only places that are getting wetter are the greens to the blues. So the high northern region, we're getting wetter as the temperature is rising. There's less snow, there's more water, but these many regions are undergoing severe drying of stress. So now we can match this. So get an idea where the drought regions are, and now have a look at where we grow food, and you can get the picture. So this is water stress in many agricultural areas by 2025 will increase. So any of the reds are bad. There's a lot more water stress in those regions. This is the effects on crop yields of warmer temperatures. So as the temperature goes up, then the down here in the reds, we have a 50% drop in yield in the dark reds, and neutral as we go into brown. So the darker the reds, the more drop in yields, projected yields of many crops. This is the balance of regions that are used for agriculture, and this is the major cereals, the attainable yields that are achieved now. So productive areas being green and less so being red. So if you match all of these images to where the droughts are, then you can see, we're in for a world of hurt the way we're going. And we're going to end up where we're going if we don't change things. The other major stress, the elephant in the room, is the global population is out of control. Around 1800, 1 billion, doubled in 123 years, and then added another billion in 33 years, added another billion in 14 years, and the gap's getting smaller and smaller. So we're at 7.5 billion, and we're projected to go to much higher. The mega cities of the world, this compares what they were in 2014 to what we expect them to be in 2030. So not much change for Tokyo, 35 million. And then we go to look at the growth in Delhi, in Shanghai, Mumbai, Beijing, Dhaka. Now, what cities are going to be affected by sea level rise, global sea level rise? Well, we've got lots of these: Beijing, Mumbai, Shanghai. Like most of these cities a lot of these cities are on coastlines. So, planet Earth, 7.5 billion and counting. With regard to be fruitful and multiply, cancel that order. Like we can't just ignore climate change. How are we going to solve these global problems if we don't address global population? You are here. This is from 2004, so this is from just over a decade ago, and here was 6 billion. So you are actually here right now, 7.5 billion. You may not want to be here. If we can't feed all the people and solve our global problems now, then we have to chop this ourselves in humane ways, well thought out ways, or we're going to go up here and we're going to collapse, and there'll be, how is it ethical to keep growing, to keep having an extra 240,000 people every morning when you wake up and have breakfast? Think about how many more people are on the earth, births minus deaths, and that number is about 240,000 every single day, about a 1.4% growth rate, compounded exponential growth. The numbers just don't add up for us. Our environment is collapsing, our population is spiraling. If somebody's living on another planet looking at us, they're saying, what, if we want to do something, if we can wait, decades, and the planet's going to implode and collapse, and then we'll go there and we'll just see if there's anything left. I mean, basically we're you know, individually we're intelligent, but collectively we're as thick as we're just doing the worst things. It's like, how do we want to destroy the planet? How do we want to destroy our future? Okay, let's go do it, right? We're doing it. So we have to change our complete economic, you know, there's all kinds of solutions. So what are some of the solutions? Anyway, procrastination. Drivers of serious government action. Bad things must happen to regular people in rich countries now. The media must report them. This is very important. These bad things are happening, but the media is still not reporting them, the mainstream media, properly. As being a result of climate change requires a change in worldview. So here's where we're going. Ice-free Arctic this decade. Extremely rapid ice-free in September. Very rapid warming, methane surges, mega drought hitting U.S. Southwest, more Katrina-like superstorms, heat waves hitting U.S. breadbasket, food prices spiking, collapse, accelerating sea level rise, ice shelf collapse, Amazon rainforest collapse. How can we deal with this? We have to treat this as an emergency now. And this is a commodity index. World War I spikes, II spikes, inflationary oil spikes. This is the Arab Spring, basically. Food prices spiked. Russia stopped exporting grains because of the massive drought there. They 40% of their grain production was 40% down. So, you know, owing to past neglect in the face of plaintiff's warnings, we have a period of danger. No more procrastination, half measures, soothing and baffling expedients of delays. We have a period of consequences. We can't avoid this period. We're in it now. Churchill, just before World War II. This is what we have to do to survive climate change. Three-legged bar stool on an emergency basis. So step one, general public, policymakers, governments, military scientists, everybody on the planet, we must get with the program and recognize our climate change emergency. Governments must declare a global climate change emergency. Then we deploy the three-legged bar stool type technologies to have a decent chance to survive the wrenching changes that we cannot avoid that are already in the pipeline. Leg one, we have to slash fossil fuel emissions to zero. No more fossil fuel subsidies, carbon taxes. How can we put carbon taxes on and keep subsidies in place? It's like, duh. Leg two, deploy carbon dioxide removal technology to lower the atmospheric concentrations. We have no choice. We have to do this. The ocean, we're going to lose life in the oceans, and we can't live without them. And the levels are just too high. We have to bring them down to 350 or below. Leg three, we need to deploy solar radiation management, SRM technologies to cool the Arctic. Otherwise, Greenland's big chunks are gonna break off Greenland, and sea level rise will rise abruptly, and the whole Arctic will become without snow and sea ice, and the entire jet stream configuration on the planet will reorganize, and we'll have to relearn how to grow food again, and life will become extremely miserable. So we have that choice. We, as quickly as we deploy these three-legged bar stool ideas, the better our chances of surviving on this planet. So thank you, and please send this video far and wide. Get as many, you know, we've got to educate people. A lot of people that watch this video probably get it. You know, that's why they're watching the video. I mean, that's not good enough. We have to figure out how to widely disseminate this information in a world where it looks like we're heading the wrong direction, at least in the US. Our political systems are, you know, we can build up policies on climate, on tax on carbon, and all the rest, and you know, we can implement them, and then a new government can come along and after 4 years. So when we finally figure it out how to do it properly, then the new government signs a couple forms on the first day, and we're done. I have this recurring vision of when Trump's first day in office, taking the Paris Agreement and lighting it on fire. I mean, how can we let one guy trash the planet like this? I think a condition of him being accepted by the electors and the military, etc., is he has to recognize climate change. Thank you. Hello, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology. I'm going to talk about the tipping points in the Earth system, and there's many of them. This schematic is from the Potsdam Institute in Germany, and it divides up the tipping points in the Earth system into three different areas: cryosphere, the circulation patterns, both ocean and atmosphere, and the biosphere components. So let's look at the ones that are most familiar to people, the cryosphere entities. So Arctic sea ice. We're rapidly losing Arctic sea ice year-round. We're going to have a year very soon when we have a blue ocean event. The models say this is going to be 2050 or 2060, but the observations show trends that are pointing to more like 2020, within the next 5 years or so. Losing Arctic sea ice in the summer by the end of the melt season, which would be September. And then once it goes for the first year, subsequent years, feedbacks kick in, and it's gone for longer and longer until it's gone probably year-round within a decade or so. Once the Arctic sea ice goes, then the melt rate from the Greenland ice sheet will skyrocket, greatly raising sea level rise. As the Arctic sea ice goes and the Greenland ice sheet goes, the Arctic is getting darker and darker and darker, absorbing more heat in the summers up there. Therefore, it lowers the temperature gradient to the equator, so the jet streams get wavier and wavier and broken up, and we get a huge increase in extreme weather events around the planet, like torrential rains leading to floods, droughts, and much stormier activity. Okay, so some other, so there's also the West Antarctic ice sheet and the East Antarctic ice sheet and basins. So sea level rise, the ice that's tied up on Greenland would raise sea levels 7 meters globally when it goes. The West Antarctic ice sheet, which is ice that's floating on bedrock that's below sea level, so it's melting very quickly from warmer ocean waters underneath, is good for another 5 meters of sea level rise, so that's 5 plus 7 is 12. Add about another 60 meters from East Antarctica. Also, as the planet is warming, the oceans are expanding, and that raises sea level rise. That's been primarily responsible for the sea level rise up to now, but the poles are kicking in big time. Also, the ocean circulation patterns, as they change, they affect sea level rise. Okay, so we've covered the cryosphere here, but we also have methane clathrates that because of high pressure and low temperatures, the methane forms in these clathrate crystal patterns of frozen ice surrounding methane. As these things thaw, the methane is released, bubbles up, can enter the Earth's atmosphere, and methane has a very large global warming potential. It's 34 over a 100-year time scale, but it's 86 on a 20-year time scale. Although recent data from this year, a paper came out and it's showing that the methane global warming potential is more like 96 over 20-year time scale. I'll do a separate video on that. There's also the methane clathrates in the Arctic, and there's also primarily on the eastern Siberian Arctic shelf, basically on continental shelves surrounding the Arctic. So as the ocean water is warming, these methane clathrates that are in the sediments under the seafloor can be exposed to large amounts of heating and release. So this is where we get, people are concerned about like a 50 gigaton burst of methane in the Arctic, say over 10 years, or maybe 5 gigatons per year, over 10 years, or a sudden release. And this would greatly increase the methane in the atmosphere, causing huge, very, very abrupt and rapid rise in temperatures. The Yadoma permafrost, the permafrost on land, okay, Yadoma, this is particularly in Siberia. It's also in the northern Canada, in other regions, Alaska. There's a lot of methane. There's a lot of organic material tied up in that permafrost. So when that thaws, bacteria breaks it down, and in the absence of oxygen produces methane, with oxygen available produces CO2. There's also methane in the wetlands, large amounts coming out, and also, you know, also, so there's also lots of human-caused methane. Like natural gas is essentially methane, so fracking and industrial processes are producing more and more methane. Okay, so that's the cryosphere. Now the circulation patterns, they can affect, so southwest of North America is very vulnerable to very, very long-term droughts. The El Nino Southern Oscillation, or ENSO, is very susceptible to change, to rapid change, to tipping, perhaps into a permanent El Nino state, or perhaps a much more intense El Nino state and a much weaker La Nina colder state. The West African monsoon is vital for agriculture and providing rainfall in Africa, and the Indian summer monsoon. These are very vital for feeding billions of people on the planet. Of course, the Atlantic thermohaline circulation, temperature, salt-driven circulation. Think of the Gulf Stream coming up, crossing, heating Europe, cycling this way. If this shuts down, it would more likely reconfigure into, instead of a loop carrying heat up to the Arctic, it would be a sort of a half loop just in this region, and everything would change in terms of heat distribution. This requires cold, salty water, which is denser than lighter, than warmer, less salty water. So as we get melt in the ice sheets, that warm water is lighter. It can shut down the AMOC, the Atlantic Meridional Ocean circulation. Okay, so those are the circulation patterns. There's also the biosphere components. We have the boreal forests in the far north. As we get warming, rapid warming, these things they can dry out, rainfall regimes change. We get huge numbers of forest fires that can take these out. And if the climate has shifted, there's not regrowth of forests, there can be savanna or grasslands replacing the boreal forest. So that changes the whole sink of carbon. There's also the Amazon rainforest, which is considered the lungs of the planet, if you like, on land. And then there's the marine biological carbon pumps in the ocean. This is the phytoplankton that suck carbon out of the atmosphere. They're eaten, there's excrement going down, they die, they go down, it enters the ocean food chain. There's evidence showing that this is getting weaker and weaker in the southern hemisphere. And of course, tropical coral reefs, not just in Australia, but you know, these coral reefs are being decimated by very, very warm ocean temperatures as we've seen. So this is the biological diversity hotspot of the oceans. This is the biological diversity hotspots of the land. So these are all being threatened in these so-called tipping points, or points of abrupt change. These can be points of no return. You know, if we knock out the Amazon rainforest, massive drought, say, which has occurred, you know, 3 separate years in the last decade or so, more and more deforestation, more and more fires, then if the climate regime has changed, then we replace this with the savanna or grasslands, and the carbon sink becomes much weaker. So there's all of these sort of tipping points that are irreversible. You know, if that happens, you can't go back, at least not in human timescales. Okay, so this is, like I say, this is from the Potsdam. If you go to the Potsdam Institute, look up Google tipping elements, the Achilles heels of the Earth system, and it explains all of these tipping elements. Some of them can be self-reinforcing or compound or cascading feedbacks. One thing happens, triggering another feedback and another feedback, and we're at great risk of crossing these tipping points. So here, this is broken down into the ice masses, and so here we go. These are all the different components, for example, and you can just click on this to get a good description of what that particular tipping element is. The circulation system tipping elements and the ecosystem tipping elements. So I highly recommend that you go to this site and just look at these tipping factors which are crucial in the Earth system, and we're very rapidly approaching the loss of Arctic sea ice, and then that will cascade to Greenland and the jet streams and all of these other different factors. Okay, the Earth system is all tied together. So we're probably within, I would say, 5 years of crossing over this Arctic sea ice tipping point. And this is why I'm saying that we have no choice but to apply solar radiation management techniques to cool the Arctic and carbon dioxide removal techniques to draw CO2 down from the atmosphere while we slash emissions. Because we're in a climate change emergency, we're going to cross these tipping points. It's just a matter of time, and it's not much time. I'm talking 5 years, maybe by 2020 even, for the loss of Arctic sea ice. So have a look at this site, it's excellent. Now, the recent climate report that came out, the 4th National Climate Assessment, Volume 1, the US report that came out, I talked about it in some previous videos, but in this particular case, I'm going to focus on Chapter 15, which are potential surprises, compound extremes, and tipping elements. So this is all about tipping points, the risks of them. Okay, so here we go, Chapter 15. So this is cascading tipping points and tipping elements. So the key findings, these positive feedbacks are self-reinforcing cycles. They can accelerate human-induced climate change and shift the Earth's climate system, in part or in whole, into new states that are very different from those experienced in the recent past or in human history. Okay, we can have an Earth so forget about this expression, the new normal. We're undergoing an abrupt change, and we're nowhere near the new normal. The new normal is a world that's much, much warmer than this world. So some of the new states might be greatly diminished ice sheets, different large-scale patterns of atmosphere and ocean circulation. Okay, so some of the feedbacks in causing these state shifts can be modeled and quantified. Others can be modeled or identified, but not quantified, and some are probably still unknown. Okay, very high confidence in this. Well, this doesn't give me a lot of confidence that there's high confidence that there's all these tipping points and so on. There's incomplete knowledge about feedbacks and potential state shifts, and these things are very, very significant and severe. Key finding 2. Okay, you can get compound events, compound tips, so you can have a tipping event where, say, the Amazon rainforest burns. It's not replaced by forest, it's replaced by grasslands. The CO2 levels spike up, causes excessive warming, sea level rise, suddenly Arctic sea ice goes, and boom, away we're off to the races. We're barreling forward, up, temperatures rise, greenhouse gas levels skyrocket. We haven't seen anything yet, we're just scratching the surface to what can happen. Wildfires associated with hot and dry conditions, flooding associated with high precipitation, rain on snow or waterlogged ground. So the result of these multiple tipping points, the result is greater than the sum of the parts with very high confidence. Okay, now these are not modeled very well at all. Also, the key finding here is that not all the processes, we don't know, we haven't quantified processes. There's a lot of unknowns still. We have very high confidence that future changes outside the range projected by climate models cannot be ruled out. We need to rely less on climate models and more on observations and more on paleo records of how quickly the planet has changed in the past in order to get a proper handle on what's happening now. So there's a systematic tendency of climate models to underestimate temperature change during warm paleoclimates. So climate models, they're underestimating what's happening now, the changes that are happening now. We really need to rely more on the observations. Okay, so let's move along here. Okay, so this is chapter 15 again. I'm going to talk about some of the details here. Since I'm running out of time for this particular video, I like to divide my videos up into 15-minute segments. I will start the next segment, part B if you like, on this particular section. Thank you.
that looks like spatially. Let's actually watch the Arctic sea ice evolve from season to season over the last few decades due to this wonderful animation from NASA. The white ice is going to be the old, very thick ice, multi-year ice. It's very robust, it's very thick. The bluer the ice gets, the thinner it is, and the more likely it is to be just seasonal ice. Ice that melts in the summer, comes back in the winter. It's not persistent. It doesn't last through the summer. And we're watching time go on, 1998, 1999. You should notice the sea ice is getting less and less, especially that multi-year thick ice, the good ice if you're a polar bear. The ice that you want is getting quite a bit less in extent. We'll look at 2007, what happened there. Now look at 2012. We have essentially no multi-year ice left. Essentially all we have now is the seasonal ice that comes in the winter and it's lost in the summer, and we're now ahead of where we've ever been in terms of how much ice we've already lost this season.
Hello, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology. And in this video, I'm going to discuss how the Arctic sea ice is being absolutely annihilated or pulverized or destroyed or massacred. Use whatever word you want to describe. It's just going, folks. And this will have global ramifications. And what happens in the Arctic doesn't stay in the Arctic. It's not like Las Vegas. The loss of the sea ice, the loss of the snow cover in June, the darkening of Greenland, all of these things are contributing to a darkening Arctic. A darkening Arctic absorbs more solar energy, heats up much faster than the rest of the planet, decreases the temperature gradient to the equator, causes the jet streams to slow down and become wavy and distorted, and greatly ramps up the frequency, severity, and intensity of extreme weather events, torrential rains, flooding, causing floods, droughts in other places. This is going to affect the global food supply very, very soon. We have a global climate change emergency on our hands, and we have to take strong action. We got to stop messing around, talking about the problem. We have an emergency situation. So I'm going to focus just on the sea ice in this particular presentation. Okay, so I killed the lights to get better contrast. So just Google Arctic sea ice graphs, and you get this type of screen here. All kinds of data. So we have this the concentration of the ice. This is September 8th. So it's basically almost real-time data. Other views of it. You can see the ice declining, the extent from different satellite sensors, different countries. There's all kinds of data on here, and this is the sea surface temperatures, the mean temperatures north of 80 degrees, all kinds of information here, very good information, so browse through it. You can click on any one of these individual graphs and get more information. So that's what I'm going to do to show you what's happening. So let's say if we click on the first image here, let me go back up to the top, click on here, this is what sort of thing that you get. You get this screen here. Now what we have is, I'm just going to move out of the picture so you can see everything. Okay, these are the sea ice maps. Okay, so this is what we have. This is the September 8th concentration. So this is solid ice. This is water here. You can see how it's breaking up here, completely breaking up, stranding this region here. So it's got this kind of shape. This is another image using false color to show different ice thicknesses. Again, you can see exactly what's going on. The ice is rapidly going. This is the Antarctic ice, of course. You know, we're at the end of summer, fall, and the Antarctic is going into spring. You can see that the concentration, there's actually gaps and things there, but we'll focus on the Arctic right now. This is the Arctic sea ice extent. I don't know why they left out 2012, I think, in this image. Here is it with 2012 was the record minimum, and we're approaching that, so we're the second lowest. Here's an interesting image. So this shows the Arctic sea ice configurations. This was back, the white area was back in September of last year, but look at the 2007 minimum. This is the extent of the ice in 2007 at the minimum. This is what we had in 2012 in the light blue line. And this is what we had in the 1981 to 2010 climatology, if you like, or the 30-year average of where the sea ice was at the end of the melt season. This is another image. So this shows you the 2012. Okay, so this is light. The 2012 minimum is what we see here with the ice, and that's compared to the 2007 minimum, which is here. Okay. This is a symbolic bear claw, by the way. You know, the polar bears are going to be scratching out the eyes of humanity because we've trashed their habitat. Okay, so let me go back here. The bear claw got too close to the touch screen. And okay, so we've got the 2007 minimum, 2012 minimum, and I've just showed you what's happening this year. Okay, so there's lots of information on this site. Okay, now let's have a look at the Bremen. So I took this image I showed you. This is September 8th, 2016. So today, basically. Generally, the minimum of sea ice is about September 15th. Sometimes it varies as it goes out to September 20th, maybe a little bit beyond, but not much beyond. Once it starts freezing up, it seems to do it quickly. But what you can see here, so we've got at least another week, possibly two, because this water is very, very warm all around, as I'll show you, which could extend the melt season. What is very, very new and novel this year, and it's not in a good way, is that the ice is so pulverized and crushed up that there's no structural integrity along the Canadian Arctic archipelago. So the very, very fine structure of the ice, it can move past each other. There's no ice blocks here on any of these channels. So what you're seeing is the ice is going through all of these channels here and melting out. So before there was a block of more solid ridged ice, thicker ice here, including some multi-year ice, and that would stop the ice from doing what it's doing. Because it's just like slush and pulverized, it's going through all these channels. So this is bad. We're losing a lot of volume through these channels, which we never had happen before. Also, there's a large amount of ice that is extending out into the Fram Strait, where it goes into the Atlantic and melts off. So we've got very thin ice around the pole. This is clearly a problem for humanity. We're losing our white pole cap over the Arctic Ocean. What's happening in terms of temperatures? So this is again September 8th. This is sea surface temperatures. Okay, so if I click up here in the Arctic, you can see that the temperatures, this is the sea surface temperatures. So when we're down here, we've got the ice, but you can see the water is warming up all around the edges of the ice. Okay, so 0 to 2, 2 to 4, if you can tell the colors, is here. 0 to 2 is this guy. This is, okay, but look at what, if you go out here, you know, look near the Russian islands, you know, 8 to 10 degrees. Actually, even higher. 10 to 12 degrees it looks like. Patches of warm water. Okay, very, very warm water. And then you go 12 to 14 degrees. You know, so these whole areas are extremely warm seawater temperatures. It's warm going down to the bottom. Don't forget that as there's less and less ice in the Arctic, there's more and more wave action. The wave action stirs up the meltwater on the surface, which is freshly which is newly created from meltwater. Okay, there's some salinity to it, but it's a lot lower because mostly it's first year ice, and the salinity, there's brine pockets in the first year ice and they release, so when it melts it's not completely fresh water. But you know, wave action mixes up the water, warmer water below comes to the surface. You know, we're under attack here. We're really under attack. You know, it's like humanity is just rolling over and not doing, like, they're giving up. I mean, they don't even realize, you know, it's the frogs in the pot sort of thing. We're no better than the frogs in the pot. This is actually, this is sea surface temperature anomaly around the globe. So a couple things, you know, no El Nino, right? We've got this ridiculously resilient ridge idea. You know, huge pocket of warm water here, which faded with the El Nino, and it's come right back as I expected, and I think mentioned in some previous videos. You know, look at the water. There's patches of water here that are 4 to 8 degrees Celsius warmer than normal. Also, the Gulf Stream up here warm. So when we go into winter, you know, expect massive snowfalls along the east coast of the U.S., you know, as this warm water evaporates, putting moisture in the air, which will then be pumped over and fall as snow as soon as we go into winter and our continent gets a bit colder in North America. Let's have a look up in the Arctic. So look at this, 4 to 8 degrees. There's patches over 8 degrees Celsius above normal. This is the sea surface temperature. It takes a lot of energy to heat water. You know, 4 to 8 degrees over these vast regions. Like, it's just, it's incredible, right? Of course, you know, all of this heat in the Arctic, it's going to take a lot longer for the ice to form. Once the minimum passes and the ice starts forming, you have to cool down all this water to below zero to get the ice, right? So the winter sea ice extent will be will be much lower. So, you know, it's only a matter of probably a few years before we lose the sea ice completely. Okay, this is temperature in the Arctic right now. So green, anything green is above zero Celsius or 32 Fahrenheit, above the freezing point. Okay, so, you know, we've got the Russian islands here. Look at this vast area. It's all above zero still. You know, it's below zero above the surface of the ice, but the ice is still melting and thinning from below. Okay, so in terms of the temperatures, this is 2016. This is the temperature anomaly in the Arctic, north of the 80th parallel. This is Danish data as a function of the day of year. So you can see fluctuation, but, you know, if you average it out, it's still well above the climatological level. And what we see is that it's extending out on this side above normal. So we can, this is 2016, we can go to 2015, 2014, see all the fluctuations here, you know, extended out a bit here. Previous minimum was 2012. It extends out quite a bit and it fluctuates quite a bit, but it's a similar pattern to compare that to 2016. And 2007 was also, you know, a lot of fluctuation, but extending out here. If you go back, say 1990, there's fluctuation, right? But it's more about the mean here. There's fluctuation. Okay, sea ice extent. Okay, let's have a look at some graphs. So this is 2016 now, September 7th. This is extent, and this is the graph coming down here. So the only year lower is 2012, but satellite information, this is satellite data. They don't tell you everything about the ice. You know, you're looking down, you're trying to assess it. This is thickness and volume. So this is the sea ice thickness. So we've got you know, there's some ice piled up here, but it's not enough to stop. All these channels are open, so the ice is going through. It's hosing out of the Arctic Ocean through those channels, which I said before was a new phenomena. Look at the ice volume. Okay, so this is 2016. We're just doing this right now. There is still a chance, you know, if the meteorology, the forecast is a week or two out, you know, more pressure lows, more storms. I'll show you that in a minute. So that could drive more ice out there, mix the water more, cause more melting. If this line continues down, boom, we're at a record year. You know, it's hard to say, unlikely, but possible. Okay, so we go to Nevin's blog. There's all kinds of stuff here. This is a PO mass volume coming down. And there's lots of good images of what's happening. So August 2nd to September 2nd comparisons. You know, what the ice was like a month ago to what it's like now. All kinds of neat stuff. You can just go here and look at these. This is called the, you know, you can see the variation here. This is over the Wrangel Arm.
Looks like spatially. Let's actually watch the Arctic sea ice evolve from season to season over the last few decades due to this wonderful animation from NASA. The white ice is going to be the old, very thick ice, multi-year ice. It's very robust. It's very thick. The bluer the ice gets, the thinner it is, and the more likely it is to be just seasonal ice. Ice that melts in the summer, comes back in the winter. It's not persistent. It doesn't last through the summer. And we're watching time go on, 1998, 1999. You should notice the sea ice is getting less and less, especially that multi-year thick ice, the good ice if you're a polar bear. The ice that you want is getting quite a bit less in extent. We'll look at 2007, what happened there. Now look at 2012. We have essentially no multi-year ice left. Essentially all we have now is the seasonal ice that comes in the winter and it's lost in the summer.